Hello everyone, welcome to my channel. In this video, I'll discuss an important topic of chemistry from the chapter Chemical Bonding. The topic is Molecular Orbital Theory of Homonuclear Diatomic Molecules. So let's start. Before going into drawing of the molecular orbital diagrams, we should know some salient features of molecular orbital theory. I have written these points for that purpose, but you can get these points from any standard textbook. So you can read from there, or you just pause the video and read it if you are interested. Anyway, I would request you to concentrate on the point number 9. Here you can see one equation is given, that is Nb minus Na by 2, which is equal to the bond order of the molecule, where Nb is the number of total electrons in the bonding molecular orbital and Na is the number of total electrons in the antibonding molecular orbitals. How we can get Nb and Na, that I will show in the respective examples. So let's start with the simplest molecule, that is H2. We know that hydrogen has the electronic configuration 1s1 as it has only one electron. So in H2 molecule there will be total 2 electrons. Now for drawing the MO diagram of H2 molecule, we will take one energy axis first and then two 1s orbitals will be placed at the same energy. Okay, because the two hydrogen atoms are there and each 1s orbital will have the same energy, and each of the orbitals will contain one electron. Now these two 1s orbitals will interact with each other to give two molecular orbitals. One will be at higher energy and one will be at lower energy. This is the bonding molecular orbital and this is the antibonding molecular orbital. Okay, now we have to connect these atomic orbitals with the molecular orbitals like this. Okay, this is named as sigma 1s orbital and this is sigma star 1s. Star indicates that this is antibonding molecular orbital, means any molecular orbital which contains star at the superscript position, you can take it as the antibonding molecular orbital. Once we have drawn this molecular orbital diagram, we can assign each of the orbitals. Like this one, 1s orbital from one hydrogen atom, so it is atomic orbital. These are the molecular orbitals and this is the atomic orbital of another hydrogen atom. Now the H2 molecule contains 2 electrons, as I said earlier, because of the two hydrogen atoms. So these 2 electrons will occupy the sigma 1s orbital. Why? Because in the molecular orbital diagram also the rules for electron occupation, that is Hund's rule, Aufbau principle and the Pauli exclusion principles are also valid. So this sigma 1s orbital will contain the 2 electrons and there will be no electron in the sigma star 1s orbital. So if we want to write the electronic configuration, then it will be sigma 1s2. So if we want to calculate the bond order for H2 molecule, then it will be Nb will be 2. Okay, because bonding molecular orbital contains 2 electrons and Na will be 0. So this will give bond order 1. And we already know this because when we write the H2 molecule, we give one single bond between the two hydrogen atoms. Right? Okay, now let's go to the next molecule and that is He2. We know that He has the electronic configuration 1s2. So there will be another electron here. So each of the 1s orbitals will contain 2 electrons each. So total electrons will be 4. Now here you can see that sigma 1s orbital already has 2 electrons. So other 2 electrons cannot be occupied here. So that 2 electrons will go to the sigma star 1s orbital. Okay. Now if we want to write the electronic configuration for He2, that will be sigma 1s2, sigma star 1s2. Okay. From this electronic configuration, we can also calculate the bond order for He2, and here you can see the bonding molecular orbitals contain 2 electrons and the antibonding molecular orbital also contains 2 electrons. So what will be the bond order? Here Nb minus Na by 2, and each of the orbital will contain 2 electrons, so this will give the bond order of 0. Okay, this indicates that helium will exist as monoatomic gas and it will not form diatomic molecule. Okay, and this is obvious because we know that the noble gases exist as the monoatomic gases and they do not form the diatomic molecule. Now let's go to the Li2 molecule. Here Li has the electronic configuration 1s2, 2s1. So total electrons will be 6. Okay. So for drawing the MO diagram of Li2 molecule, obviously this will be there because 1s orbitals are there. So sigma 1s and sigma star 1s molecular orbitals will be there. Now another orbital will be coming, that is 2s orbital, and this 2s orbital will also give sigma 2s and sigma star 2s, that is one bonding and one anti-bonding. Now if we try to put these electrons in the diagram, that will be like here sigma 2s orbital will contains the extra 2 electrons. Now let's try to write the electronic configuration. Here you see sigma 1s contains 2 electrons, that is sigma 1s2, then sigma star 1s2 and then sigma 2s2. So what will be the bond order? It will be 4 minus 2 by 2 equal to 1. 4 because the sigma 1s and sigma 2s both are bonding and that contains 2 electrons each. So total will be 4 electrons in the bonding molecular orbital and 2 will be in the anti-bonding molecular orbital. So it is giving 4 minus 2 by 2 equal to 1. Now let's go to the Be2 molecule. Be has the electronic configuration 1s2, 2s2. Okay. So another electron will be there in the 2s orbital. So the total electrons will be 8. Now sigma 2s is already occupied, so the another 2 electrons will go to the sigma star 2s orbital. So what will be the molecular orbital diagram electronic configuration? It will be sigma 1s2, sigma star 1s2, sigma 2s2 and sigma star 2s2. Okay, so there are 4 electrons in the bonding molecular orbital and 4 electrons in the anti-bonding molecular orbitals. So what will be the bond order? It will be 4 minus 4 divided by 2 equal to 0. After B2 molecule, that is from B2 onwards, the diagram becomes little bit complicated because the 2p orbitals are also involved. Now before drawing the diagrams, first you concentrate in this diagram. Here you can see for boron, carbon and nitrogen, the energy gap between the 2s orbital and the 2p orbitals are less. Red line is the 2s orbital and the blue line is the 2p orbital. Okay, but for oxygen and fluorine, this gap is considerably larger. So what is the outcome for that? We need to draw the molecular orbital diagram with sp interaction for B2, C2 and N2. But for O2, F2 and also for Ne2, we don't need to consider any sp interaction. Okay. Now first let us see the molecular orbital diagram without the sp interaction. Here I have not shown the sigma 1s and sigma star 1s. Instead of that, I have written KK cell. This indicates that the sigma 1s2 and sigma star 1s2 is there. I have started with the 2s orbital only. If you have space, you can draw the sigma 1s and sigma star 1s also. But if you don't draw, that is also okay. Just you write that KK cell is there. Now, the 2p orbitals will also be involved in the diagram. So, and that will produce sigma 2px orbital. Px orbital will give the sigma 2px orbital, and the other two, that is the 2py and 2pz, will form the pi orbitals. So sigma 2px orbital will have its antibonding part, that is sigma star 2px, and pi 2py, pi 2pz will also have its antibonding part, that is pi star 2py and pi star 2pz. Okay. Obviously, we have considered that the x-axis as the molecular axis. Now, this is the diagram without the sp interaction. Now, when we consider the sp interaction, the diagram is changed. Here you see the most important change is the energy ordering. Okay. Now, here it's the molecular orbital from 1, 1, 1 and then 2. Now, here you see 1, 1, 2, then 1. Okay. So, when we are considering O2 and F2 or even any two molecule, then we have to write this one without the sp interaction, but for B2, C2 and N2 we have to consider this diagram. So this is the diagram with sp interaction, and we can say this is for B2, C2 and N2, and this one is for O2, F2 and Ne2. Okay, now using these diagrams we will try to find out the bond order and other properties for these molecules. Okay, let's go to B2 first. As I said here that we have to draw the MO diagram for B2 with sp interaction. So this will be like this. Okay, the boron atom has the electronic configuration 1s2, 2s2, 2p1. So we have to consider total 10 electrons in the energy diagram. Here already 4 electrons are there, and the another 6 electrons will be occupied in the higher energy molecular orbital diagram. So this will be occupied like this. The sigma spx1 will be with the 2 electrons, sigma star spx1 will have also the 2 electrons, and the pi 2py and pi 2pz will contain 1 electron each. Okay, so the electronic configurations will be sigma 1s2, this is coming from the kk cell, sigma 1s2, sigma star 1s2, then sigma spx12, sigma star spx12, pi 2py1 and pi 2pz1. So now you calculate the number of electrons in the bonding molecular orbitals. This will be 2 plus 2, then another 1, 1. So total electrons will be 6 in the bonding molecular orbitals, and total electrons in the antibonding molecular orbitals will be 2 plus 2, that is 4. So what will be the bond order? It will be 6 minus 4 divided by 2, and that will give the bond order of 1 for B2 molecule. The next is magnetism. Here earlier I have not discussed any magnetism. Just remember, if there is any unpaired electron in the diagram, then the molecule will be paramagnetic. If there is no unpaired electron, the molecule will be diamagnetic. Here 2 unpaired electrons are there in the pi 2py and pi 2pz molecular orbitals. So this molecule, B2 molecule, will be paramagnetic. Now let's go to the C2 molecule. Here also we have to consider the molecular orbital diagram with sp interaction, as I said earlier. So now the carbon has the electronic configuration 1s2, 2s2, 2p2. So total there will be 12 electrons. How that will be occupied in the MO diagram? You can see here. Now 2s will also contains 2 electrons, and the 2p orbitals contains 2 electrons. So total 12 electrons. Out of that 12 electrons, 4 are there in the kk cell, and 8 electrons will be occupied in the higher energy molecular orbitals, and this will be like this. Okay, so now you can see here the pi 2py and pi 2pz earlier containing 1 electrons for the B2. Now it are all evenly paired. Okay, so what will be the electronic configuration? It will be sigma 1s2, sigma star 1s2, sigma spx12, sigma star spx12, pi 2py2, pi 2pz2. So what will be the bond order? Bond order will be 8 minus 4 divided by 2. If you count the total electrons in the bonding molecular orbital, you will get 8 electrons, and total electrons in the antibonding will be 4. So this will give the bond order of C2 molecule as 2. Now here, as I said, these are paired electrons, so C2 molecule will be diamagnetic. Now let's go to the next molecule, and that is Ne₂. Here also we have to consider the molecular orbital diagram with sp interaction. Nitrogen has the electronic configuration 1s2, 2s2, 2p3. So there will be total 14 electrons, and 4 electrons will be in the Kk cell, and other 10 electrons will be occupied in the higher energy level molecular orbital diagrams. Okay, and that will be occupied like this. So we can write the electronic configuration for Ne₂ molecule as sigma 1s2, sigma star 1s2 that are coming from the Kk cell, and then sigma spx12, sigma star spx12, pi 2py2, pi 2pz2, and sigma spx22. Okay, so in the bonding molecular orbitals there will be total 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10, and in the antibonding molecular orbital will be 4. So the bond order will be 10 minus 4 divided by 2, and that is 3. Okay, we know that because when we write Ne₂ molecule we give triple bond in between the two nitrogen atoms. Okay, so and that can be predicted by the molecular orbital theory. Now in the diagram there is no unpaired electron, so Ne₂ molecule will be diamagnetic. Now the next molecule is O2. Here we don't need to consider the sp interaction. We can draw the molecular orbital diagram without the sp interaction as I discussed earlier. Okay. Now O has the electronic configuration 1s2, 2s2, 2p4 as its atomic number is 8. So there will be total 16 electrons for the two O atoms, and 4 will be in the Kk cell, and other 12 electrons will be in the higher energy molecular orbital diagram, and that will be occupied like this. Okay, so the electronic configurations will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2px2, pi 2py2, pi 2pz2, pi star 2py1, pi star 2pz1. Okay, so the bond order will be 10 minus 6 divided by 2, and that will be 2. And we know that because between the two O atoms we always write double bond. Now the magnetism, here two unpaired electrons are there in the molecular orbital diagram, so O2 molecule will be 2 electron paramagnetic. Now the F2 molecule, here also we will draw the molecular orbital diagram without the sp interaction, and the fluorine atom has the electronic configuration 1s2, 2s2, 2p5 as its atomic number is 9. So there will be 18 electrons total in the molecular orbital diagram. 4 will be in the Kk cell, and other 14 will be in the higher energy molecular orbital diagram like this. So the electronic configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2px2, pi 2py2, pi 2pz2, pi star 2py2, pi star 2pz2, and the bond order will be 10 minus 8 divided by 2, as total electrons in the bonding molecular orbital are 2, and the total electrons in the antibonding molecular orbitals is 8. Okay, so the bond order will be 1. And you can see from the diagram that there is no unpaired electron in the MO, so F2 molecule will be diamagnetic. And the last one for this video, and that is Ne₂ molecule. Here Ne has the electronic configuration 1s2, 2s2, 2p6. So there will be 20 electrons in total. Okay, and the electrons will be occupied like this. So the molecular orbital electronic configuration for Ne₂ will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2px2, pi 2py2, pi 2pz2, pi star 2py2, pi star 2pz2, and sigma star 2px2. If you calculate the total number of electrons in the bonding molecular orbitals, it will be 10, and also in the antibonding molecular orbitals will be 10. So the bond order will be 10 minus 10 divided by 2 equal to 0. Okay, this indicates that NE2 molecule does not exist and Ne exists as the monoatomic gas. This is already we know because all the noble gases exist as the monoatomic gas. As for helium also, we have got the similar result. The summary of this video, here you see we have drawn the molecular orbital diagram from H2 to Ne2, and MO diagram indicates that He2, Be2 and Ne2 should not exist. Okay, other molecules should exist, and in the third column the bond order between the two atoms have been shown, and the magnetic properties for those molecules have been shown in the last column. Okay, I hope you all understood what I have discussed in this video. If you have any question, you can write in the comment box. I will try to answer those questions. Okay, thank you all for watching my videos.